When I was young, I was fascinated by planes and wanted to be a pilot. I first got a chance to fly on a plane when I was in middle school. And what I remember is how smooth the ride was. I did not even feel that we were moving. When I grew up, I had a chance to look inside the cockpit and I saw how complex it was. But still, the experience of flying was made smooth and easy for the passengers. And that is how Google Cloud Platform operates. It has complexity inside, but for the user, it is simple and easy to use. And it is reliable like planes too. Hi everyone, I'm Amit Singhal, technical lead at Google. Today, along with my colleagues, we'll talk about how Google's software-defined approach behind its infrastructure and products make it resilient, scalable, and high performance. We'll deep dive into Andromeda virtual networking and also talk about front-end systems that route all incoming traffic. In the end, we'll talk about some of the networking products. Google Cloud Platform at high level comprises of following: compute, which has compute engine, app engine, container engine, and cloud functions. Then we have storage, which has several products like Cloud SQL, Bigtable, Cloud Data Store, Spanner, etc. Networking, with infrastructure for virtualization and load balancers, and several products like Cloud VPN, routers, firewalls, etc. Analytics, with products like BigQuery, Dataflow, Dataprog, machine learning, etc. One key advantage Google Cloud customers get is reliability and scale of running on same shared infrastructure that powers all Google services like search, ads, maps, Gmail, etc., built with years of experience and state-of-the-art technology. Google has been a pioneer in large-scale distributed systems for more than a decade. Many of Google's innovations have completely changed the standard computing paradigms and spawned new industries. MapReduce started big data revolution. Cloud Dataflow is built over that. Bigtable was one of the first NoSQL database implementations, and Cloud Bigtable is built over that. Then we have Cloud GCS over Colossus. Cloud BigQuery is built over Dremel. Spanner is a wide area consistent database service that allows you to run transactions across the globe, and Cloud Spanner is provided over that. All these services are provided through GCP APIs. We use software-defined approach across all verticals of cloud, and they share similar concepts. We would love to talk about all the areas, but in the interest of time, we'll focus more on the networking in this talk. Google is constantly innovating in networking space. This is a timeline of the major milestones. We have taken software-defined approach early on in almost everything we do. Maglev is a software load balancer that routes all incoming traffic to correct backends. B4 is our WAN network built using SDN principles. Jupyter is our software-defined data center networking. And Andromeda is our software-defined network virtualization technology. Why Google Cloud Networking? It provides high throughput up to 16 gigabit per second and under 100 microsecond latency between VMs. You can spin up thousands of VMs within few minutes, and we provide hitless upgrade and feature rollouts without impacting customer workloads with our VM migration technology. One of the key advantages of our networks are that they are global, which allows customers to have VMs in different regions communicate over private IPs. And we provide network functions as a service like load balancing, routing, security, CDN, etc. We talked about why, and now let's look at what is Google Cloud Networking. Like I said, we at Google use software-defined networking, SDN, in everything we do for networking, but Google Cloud Networking is not just that. First of all, it is built upon our state-of-the-art WAN connecting our state-of-the-art data centers. It is network virtualization and isolation using SDN principles. It has to scale to support thousands of VMs for thousands of customers and provide customizable functionality through APIs. All this together make Google Cloud Network. So software-defined network virtualization, what are the benefits for user? It provides faster provisioning times with centralized controller, faster rollout of new features without depending on new hardware, high availability using hierarchical control plane. In next few slides, we'll talk about how virtual networks are different from physical networks and what are the unique challenges that create. Overlay of virtual networks over physical network, and we'll also talk about our centralized hierarchical control plane. Some high-level background on how physical networks look. You have racks of servers, we call them hosts here, shown in green boxes. They connect to top of the rack switch TORs. TORs connect to each other through one or more routers in the middle. Important property of these networks is address aggregation and locality. That limits the radius of layer to broadcast domain, and that is also used by distributed routing protocols and switches to learn and make forwarding decisions. With cloud, physical data center networks become multi-tenant. You can imagine there is a logical switch per virtual network. Now, one way to support this is by extending the whole stack to become aware of multi-tenancy and use tenant key. In this case, we call it VNet here for virtual network, in making all forwarding decisions. Now, this need changes to physical switches and routers, and also make routing protocols to carry this new information. But even if we do that, what makes this approach difficult is that as customers spin up new VMs, they can be scheduled anywhere on the physical network, depending on the availability. And there is no location-based address aggregation. Network virtualization takes a different approach. Instead of relying on dynamic discovery-based protocols, it creates a logical overlay for each customer, hiding details of the physical network. Using encapsulation and host port information for each VM, point-to-point flows are created between VMs. Now, centralized controller is key to implementing such approach. Now, let's look at workflow for VM creation and network provisioning. In this case, owner of the orange network wants to add one more VM. He sends the request to configuration manager, which calls compute control plane to start a VM on some host with available capacity. That information is given to configuration manager, which calls the network control plane with the host port information of the newly created VM. It then sends a message to all hosts which has VMs from this network, and point-to-point flows are created from this new VM to the existing VMs. In this slide, I'd like to emphasize the hierarchical implementation of our configuration and control plane. Configuration plane serves all user requests by calling appropriate backend modules. It is divided into 3 levels: global, regional, and zonal. Even backend control plane is divided into 3 levels: global, regional, and zonal. User requests are routed to various backend jobs at different hierarchies. Now, goal is to keep most configuration and provisioning at zonal level to limit the blast radius of any failure, and then regional, and only few services to be global when necessary. We talked about configuration. Now let's look at control and data plane. Fabric Manager gets all requests for network provisioning. Again, tasks are divided at regional and zonal level. There are VM controllers, which manages all the VMs inside customer network, and these VM controllers are zonal. It creates flows between all the endpoints on a virtual network so these endpoints can communicate. Our next speaker will talk in more detail about this part. There are cloud front-end tasks that provide connectivity to Google services for VMs through internal network without having to traverse through public network. Endpoints inside virtual network can send traffic to internet through Google Edge routers. And finally, all incoming traffic first hits network load balancer and appropriately routed to correct endpoint in either customer network or Google front-end tasks for Google services. And now I'll hand over to my colleague and next speaker, Krishnan, to talk more about Andromeda virtual networking.
Thanks, Amit. In this portion of the talk, I will be covering details on the network virtualization infrastructure that powers GCP. This is a great opportunity for us, especially me, to represent the work of an amazing team here at Google. So network virtualization for GCP internally is known as Andromeda. Andromeda powers the virtual networking infrastructure and a lot of our network product offerings. Amin Vadat, Google Fellow, has presented on Andromeda at ONF earlier. And today, we will be uncovering the nuts and bolts of how Andromeda is actually built, especially its core features that allows us to build scalable and high-performance systems. So what you see behind me is GCP's network. It is one of the largest networks among cloud providers. It is globally spread out. There are 6 regions, 18 zones, and we will be announcing 12 more regions in 2017. Network virtualization is to make it easy for you, the customer, to leverage this amazing network. This talk is in 2 halves. First, I'll be doing a deep dive into our control plane. First, I'll be talking about how we provide isolation across virtual networks. In this example, there are 2 virtual networks which share the same physical infrastructure. I will be giving details on how network virtualization allows these networks to have their own tenant space. We will also be talking about how we can scale up on demand. GCP, we have done experiments where we can show 100K VMs can be spun up in 184 milliseconds. I shall also be going into details on how we achieve our high availability targets. We can do 3 nines in a single zone, 4 nines in a region, and 5 nines globally. Next, I'll also be going into details about our unique data plane. Our data plane has core network functions baked directly into it, for example, load balancing. We're also constantly evolving, and we are building new network functions into our data plane. I'll be talking into details on how we achieve that with using live migration and also what we call hitless data plane upgrades. So let's dive right in. As Amit mentioned, our control plane is built as a hierarchy. Sits at the very top where we call cluster manager. The cluster manager performs many tasks. It is responsible for configuring things like storage, compute, and in our case, networking. Below that sits the fabric manager, and you can see a theme going on here. It's again split up into regional and zonal control planes. Andromeda comes below it, which is VM controllers. And what the fabric manager and VM controller's job is to expose a high-level API, which is used to configure the virtual networks and also different network functions. Right below it sits the OFE, which is the open flow layer. It takes our API abstractions and then converts them into open flow programming constructs that we can use to program a switching layer. The switching layer shown here is built directly into each VM host. It has a programmable switch, which is based on Open vSwitch, and it has a core data plane, which is responsible for packet processing. So now let's take a deeper look on how we actually achieve the scale of our control plane. I've zoomed in here a zonal view of our control plane and a single host it's managing. A zone shares the same hardware failure domain and also has the same network connectivity. To guard against machine failures, the VM controllers are replicated. It has one singly master, Paxos-selected master, and 2 standbys to take over at any given time. We've also sharded the OFEs, and a single OFE maintains shards, multiple VM host shards. And we take the sharding concept one step further. We replicate our entire control plane so that each VMC also manages another racks or another set of hosts. This allows us to smear processing across these different replicas. Finally, this also allows for easy horizontal scaling. If you want to add new capacity to our zones, let's say we bring up a whole new set of racks, all we need to do is spin up a new replica of our control plane. Voila, you have a new capacity we can announce. It is as simple as that. So as GCP has grown and our offerings have expanded, the network programming has become more and more complex. We started off with a very simple model. It's a pre-programmed model. It looks something like this. It's a full mesh. It is very simple, consistent, and predictable to think about in latency. But it has one problem. It is quadratic scaling in terms of VMs. So anytime for a network, if you're going to add a new VM, you have to do this full mesh. That means you have to go ahead and program OpenFlow rules in every single VM host. We can do better than that. So we started looking. The first thing we evaluated was the traditional OpenFlow model, where the control plane waits for the first packet, and based on the packet, we install our flows. Now this scales much better than the pre-programmed model, but it has unpredictable latency, and you can imagine why. It is dependent on the control plane capacity. It also exposes the control plane to packet floods from the host. So what we instead did is we combined the best features of all these different things, and we came up with a model what we call hoverboards. Hoverboards are a software gateway, and you can think of this as a default router in your network. We don't need to pre-program our flows. As soon as the VMs come up in a network, the packets start egressing and ingressing through the software gateway. So there is really no warm-up time. Small networks remain as before. We borrowed this from the pre-programmed model. As I mentioned before, it is simple and it's consistent. For this hoverboards, as flows that are going through it grow larger, we have also added the ability to offload them directly back to the host. And this allows our software gateways to scale, as well as giving predictable latency and throughput. So from this, I'm going to move on to the data plane now. So we've been working on this for a while. The first step was Andromeda 1.0, where our data plane was in the kernel, and it had Open vSwitch. To that, we added offloads for performance, and we introduced live migration. This was Andromeda 1.5. Next is what we have the current version, which is 2.0. It is a large evolution, where we moved the entire data plane from the kernel to Userspace. With it came a huge boost in performance, and also a large increase in release velocity. And I'll be talking about how that we achieved that. In the next few iterations, we're pushing hard on hypervisor bypass. The first version that we're working on right now is 2.1, which allows the guest OS to bypass the hypervisor and talk directly to a Userspace NIC. And in the future, we'll have full bypass, where the guest OS will be directly talking to the hardware NIC, giving you full hypervisor bypass. So one of the goals when we built this new data plane in Andromeda 2.0 was to enable native hardware performance in software. So the way we did that is we introduced what we call a fast path. And a fast path has a single CPU that's busy polling and is optimized for performance. It can sustain up to 2 million packets per second. CPU-intensive operations, we moved it off the fast path into what we call coprocessors. Coprocessors have this unique ability to scale with the technology we call CPU attribution. And finally, all this is controlled by the on-host control plane using Open vSwitch. So you might have a question as to why did we build this in Userspace, and I should mention 3 distinct advantages. The first one is security. Our data plane runs without any root privileges. Unlike a monolithic kernel, it also has a very small attack surface because it's built for one purpose. So we can do continuous fuzz testing on it. It also comes built with ASLR and has stack protector canaries to prevent against memory corruption. It also gives us improved robustness. So if you think of this, if you have a kernel networking stack bug, it'll take down your entire machine. And in this case, it's a user-space process, so it'll just come right up. Finally, one of the biggest advantages we have is rapid releases. We can upgrade the entire data plane underneath without having to either live migrate the VMs or do a machine drain. It's not just performance that we optimized for. We also wanted a fully programmable data plane. What I've shown here is a data plane with a flow table. Now the flow table can take a 5-tuple or a 3-tuple key match and has extremely extensible packet actions. The VM controller has full control over this. It can program it, and in this case, It is programming it through OpenFlow, through Open vSwitch, which is programming, let's say, an NCAP and a DCAP action. We also have extended the Open vSwitch. So we have Google extension frameworks that allows us to provide stateful functions like sticky load balancing. We can do things like stats and filtering and policy enforcement directly inside the Open vSwitch. We also have extended the coprocessor API. It's extremely extensible. Anything that requires inline packet processing, for example, traffic shaping, DOS and abuse, we have built inside the coprocessor, and it's API exposed as well. And any new features we're actively developing are getting implemented in this coprocessor framework. So next, I'm going to talk about performance. So what is the advantage that you get when we move from Andromeda 1.0 onwards? So first up, throughput. We improved throughput by over 5x from Andromeda 1.0 to Andromeda 2.1. So currently, without throttling, you can get 25 Gbps on a 40 G NIC setup. Just note though, customers are throttled at 16 Gbps overall. This is to provide consistent performance across different hardware platforms. We also improved latency. TCP round-trip latency reduced by 7x when we moved from Andromeda 1.0 to Andromeda 2.1. Finally, CPU efficiency. We measure CPU efficiency as cycles per byte, and this combines the receive side guest, the receive side host, even the sender side host and sender side VM. And we improved it by a factor of 8, giving more CPU to the guest to use for other functions. And with that, we wrap up the Andromeda section of this, and I'll be handing over to my colleague, Assar Westerlund, to discuss how we take the software approach all the way to the front.
Thank you, Sri. I will be talking about how this cloud networking fits into the internet at large. So where do we connect to the internet? This is a map behind me here of where we have POPs, or points of presence, where we pair with other networks. Our global network spans the world and connected data centers, but to make it sure it's truly useful, we want to connect it to ISPs and be close to the users. We are peering with ISPs at over 100 interconnection facilities and at about 90 internet exchange points. About 80 of those are used for the load balancing and CDN features I will talk about. As an indication of the distances here, and being network folks, we measure it in milliseconds. Sodexis just did a third-party evaluation of our CDN for the cloud offering, and their numbers are that the median latency for fetching an object from the CDN is 42 milliseconds across the world. And the 90 percentile of that is 148, so not that much higher. So there's, and like lots of other things that we care about the tail as well. So what does it look like? This is an example here behind me of how you would configure global load balancing in the Google Cloud. One feature we have is that we have a global IP address. So when you configure a load balancer, you get one global IP address that is valid for all the users, and more importantly, it gets good service to all the users. So this means you don't have to do any DNS-based load balancing. The only thing you need to do is put in a record in your DNS server of your choice with that address. And as you can see on the picture here, your users will get redirected, will get content from as nearby as we can make them. So the Des Moines users get connected to US Central, and the Mumbai users get connected to an Asia region, regardless of anything you have to do. The only thing you have to do is to make sure they use this IP address. And this is, again, like my co-presenters talked about before, built on the existing shared infrastructure that we at Google use for all the Google services that you are used to. And nearby the user, we allow you to have a CDN. It's a one checkbox option if you want to have CDN with your load balancing offering. We can do different routing on a per request level on each URL, and I will talk more about that. And the latency matters for us. Latency matters for users of web services. We have known this with search, for example, for a long time. And it also matters for microservices. If you build your infrastructure so that you're calling different things, being able to get back soon is important. So that is something that we care about. So this is an overall picture of what it looks like at the edge. Your phone in the ISP's network on the left here is connecting to your global IP address. We pair with this ISP, either directly or indirectly at some point using the border gateway protocol. And in the edge POP, we have a little bit of infrastructure so that we can serve cache content from there, from the CDN, and we can terminate the TCP connection from the user there, which brings a performance advantage in that it's a shorter connection, retransmits are much faster, and you get better performance of it. And then over on the right, further away from the user in the NL case, you have your data center where you run the actual VM jobs. So I'll go into more detail on these steps. So the advantage with doing this in software, like you heard from Amit and Sri, is that we are very used to building systems that scale out. We scale up the number of components. We can handle larger amount of traffic, larger amount of volume. It scales with new hardware that gets better. And since the system is built to deal with failures, one of those not being there, we just work around that, and we keep going. Also, this is a similar mechanism that we use for pushing updates. We can take one component off, we can push a new version of binary to it, bring it back up again, it gets part of the mesh, it gets running again. And we can do rolling upgrades that way without anybody noticing that anything was down. So at some point we start with version X, and then slowly, assuming everything goes well, we end up with the version X+1 with the new features. And if something doesn't go well, we just go back to version X again. And everything here being described here is also integrated into the configuration manager that Sri talked about earlier. So all these components get orchestrated together to make sure the whole data plane works from end to end. So how does it work to have just one global address that is usable from anywhere? Mostly people talk of this as an anycast address. The large feature we have done here, though, is to make it stabilized so that if things change and routing changes over time, that doesn't have an impact. The way this works technically is fairly simple. We announce a block of addresses to all our peers for BGP. For each ISP, they get to figure out what routes do they have for this block to reach to Google. And oftentimes it's a long list of different ones. They get to choose, and then typically they choose the shortest path, which is the smallest number of hops. But they also have a number of other paths they can use if that one isn't available for some reason. So in general, your user's traffic ends up at the nearest POP by network distance, which should be not that far away. And then there's a fallback if that POP isn't available or it goes somewhere else. Routing flaps, which means that routing changes over short periods of time and goes back, is fairly common, which makes it hard to deal with these anycast addresses for TCP in general. So we have a special mechanism that we have built to deal with that I'll talk about later. So these are the things that we put in a POP. We have two routers for redundancy that are the connections to the other networks. And then we have two more steps. First, we have a network level load balancer that does routing on TCP connections. We call it Maglev. This is something we built in-house. So the function of that is to map each incoming user's TCP connection to one of the next set of boxes. The GFE, or Google Frontend for short, is the HTTP-based load balancer that we built. So that is the first level that can actually take the URL apart and act based on the full contents of the URL. We installed CDN in these POP applications as well, so that for cache content we can serve it very quickly back, and we don't even need to send it to a data center. So let's talk more about the Maglev. The Maglev is basically taking a 5-tuple hash and mapping that to one instance of GFE. So that means that we keep that connection at the same instance. We have all the cache content, all the state, and that point, as long as we can. So the goal is to each user, and in a load balanced fashion, hits one particular GFE. And there's multiple mechanisms that go into making that happen. Once we have established a connection, we keep track of where we sent that particular user, and we'll keep sending it there to make sure that's a stable connection. If it's a new connection, so we haven't seen it before, then we use consistent hashing to make sure we have a uniform way of making that decision across the board across this ever-changing set of load balancers. To deal with these route flaps I just mentioned before, we have a map that says for each client prefix, where do we expect this to land? And if a maglev gets traffic that isn't supposed to land there, we'll forward it to the other maglev. And once that route flap isn't there anymore, the user won't see any difference, but the other maglev will be doing the work now. Maglevs are only on the inbound path, so all traffic that goes back to the user goes out directly, which makes them more efficient. They only have to deal with one side of the flow. And if you do network level load balancing for your cloud features, the maglevs will be the ones sending traffic directly to your VMs. And they get to know what IPs to deal with from this configuration manager that we talked about before. So these are all software, runs with kernel bypass on normal servers, and they can do this at line rate. So this is the flow for each maglev. For each incoming packet, it looks at the target IP address and says, is this an address I'm dealing with? Am I doing load balancing with this address? If not, we can just drop it. If it is, we look it up in this map that says, for this prefix, it should be in this location. And if that location is not me, well, I know where to send it, and I will pass it on to that one, and that one will do the right thing with it. And this, we rebuilt this client IP map so that we know where to expect traffic. And then we look it up in the connection tracking and says, have we seen traffic from this client before? If so, we know where to send it. If not, we use consistent hashing to figure out where it should go, and we annotate that in the connection tracking, so subsequent packets on that TCP connection can go there directly. The next step is in the edge POP is the GFE. It's a proxy or a reverse proxy. So it terminates the TCP connection, which, as I said before, helps with making it a short connection to the user and improving latency and improving recovery time if we get any drop packets on that link. It terminates HTTP, and by HTTP I mean the whole family of HTTP-like protocols. So 1.1, 2.0. gRPC is a Google RPC system, open source, built on top of HTTP 2.0. And QUIC is basically the next version of HTTP running on UDP instead of TCP. Once it actually has the full hostname and the URL, it knows what is cacheable and what's not cacheable, and it can consult the cache and see, do I have this object cached? And if so, I can serve it from there directly. It can also do different things depending on the full URL, so you can have different mappings for different parts of the URL space. By default, it will send traffic to the nearest region, again, to reduce latency. If that region is at capacity and that can't handle it, we'll send it somewhere else. And that capacity can either be you configure each VM saying, hey, this is how much traffic it can handle, or you can just look at the CPU load and say, oh, well, these VMs are overloaded, we should not be sending them more traffic. And to reduce latency, we also health check VMs at a time before we send them any traffic, so we know that they're up and healthy, so that those requests don't have to wait. So here's an example. Assuming you have a website where you have your assets, your images, your HTML, your CSS, your JavaScript, instead of serving them from a web server, you can just put them in a storage bucket and tell us when you set up your load balancer, everything that starts with static, please go and fetch it. It's in this storage bucket. And that means that we don't even need to go to your VM and bother it at all about these requests. We can send them directly to the storage, which is scalable solution that grows by itself. And you can have different portions of the URL space can also get sent to different set of VMs. So if you have some level of different content for different processing, you can send it to different places. So this is the overall picture. The GFE over on the edge, after having consulted the CDN and knows it's not a cached content, it consults the global load balancer at the bottom there, which will tell it, well, we have capacity in this zone, or we have capacity in this zone. And the GFE also tells the global load controller how much traffic it has sent, so they can update its accounting and know not to send too much traffic. In each zone, inside a zone, there's a health checker that goes and checks the VMs that are registered to be backend for the load balancer to make sure that they are healthy. And they reports that back to the global load controller, so we wouldn't send traffic to a VM that is not up yet or not running healthy. From the networking point of view, the GFE looks to your VMs like a normal machine on the network. It is using a public IP address that's not routable, and you can think of it as GFE is actually forming part of all your VNIDs, but GFE can tell apart one from the other. So from your VMs and your web servers running on your VMs point of view, it just looks like a normal host on that network is sending it traffic. And this is all using the virtual networking from Andromeda that Sri already talked about. So to tie this back, what we really care about and would like you to enjoy and your users to enjoy well is low latency. And we have built this in multiple different ways. First of all, we have an extensive network of peering points so that we end up being close to your users. If we can't serve from CDN and we have to go back to VM, we'll go to the nearest region, again, to reduce latency. We make sure everything is warmed up so that you already had on the connection, we are ready to send it on, we have done the handshakes, and we know that that VM is healthy and serving, and we can send it a request. And we also done a bunch of work on different protocols, the list of HTTP family protocols I listed earlier that are all aimed at reducing the latency. So as an example here, we did a load test across 3 different zones where we pushed up the load test to 1.3 million requests per second. And to me, the impressive thing here is not that line, which is great, but you can see how quickly we're able to get to that line, right? We were able to scale things up very quickly. Now, next up is Amit is back, and he's going to talk to you how we have built all kinds of different networking products based on this infrastructure.
Thanks, Assar. Let's look inside the software-based design of some of our networking products now. First product I'll talk about is Cloud Router and VPN. BGP and IPsec VPN is often used by enterprises to provide multi-site connectivity. One of these sites can also be your cloud provider. In a typical deployment, VPN and BGP are in the same hardware box. BGP routing protocol automatically learns about the changing topology on the remote side and programs the hardware box with forwarding decisions for outgoing traffic. And all servers or VMs send traffic to this box, which then encrypts and sends it to the other side. In GCP, there is no hardware box involved, and BGP and VPN run in separate tasks, providing control and data plane separation. Cloud Router task that runs BGP programs the learned routes from the remote peer directly on VMs and tell VMs to send traffic directly to the right VPN task for those destinations, which then sends it to the other side. Our implementation provides isolated and customizable routing and VPN functionality for each customer running inside their own virtualized network. We maintain a pool of free router and VPN tasks which are ready to be allocated to any virtual network when the request comes. When Cloud VPN request comes, it is forwarded by a config manager to the VPN manager, which then allocates a free task for this VPN. Information about this allocated task is also sent to Fabric Manager, which then further programs other modules downstream. Now, when the Cloud Router creation request comes, it is forwarded to Routing Manager, which again allocates a free routing task, and the information is sent to Fabric Manager for programming the data plane. At the end of this, there is a direct connectivity between your VMs, router, and VPN as part of your virtual network. Now let's look at what happens in case there is a failure. If for any reason router task fails, Routing Manager identifies that and allocates one more from the free pool and also updates Andromeda flows. Routing manager and data path also preserves the routes for BGP whole time, so traffic is not impacted. Internet load balancing. This is a typical multi-tier deployment for web services. There are front-end web server for serving UI and static content, back-end application and business layer for dynamic content processing, and both these layers need to scale out with demand. You configure external load balancer over public IP to distribute requests to your front-end instances, and front-end will further need to distribute these requests for dynamic processing to one of the back-end servers. And we want to do this in a load balanced way. And for this, we provide managed internal load balancing over private IPs. Here we compare how our implementation differs from a typical load balancer. Normally, there is a hardware box or task to which all traffic is sent, which then load balances it between available backends. Now, drawbacks for this approach are single point of failure, and load balancer itself can become choke point for handling all traffic. Therefore, we got rid of the middle box. Each client using 3 or 5 tuple consistent hashing picks a backend for each connection. Load balancer is provisioned inside each client as a customizable network function. Internal load balancer is fully programmable through API. Let's look at the configuration flow. In addition to components for configuration and control plane we have seen so far, there is health checking infrastructure. When you configure load balancer with list of backends, health checker is asked to monitor their health. Updates are sent to VM controller, and based on those, it programs client VMs with the right load balancing configuration. Client can then send traffic directly to the backends. Now I'll talk about network peering. This is a new feature which was recently released in alpha and will be in beta soon. It allows you to peer 2 networks so that VMs in those networks can communicate with each other. Common use case would be providing software as a service over GCP platform. In this example, say Google wants to provide a cloud service to its consumers, consumer 1 and consumer 2. For reasons of isolation, billing model, etc., it is preferred to spin up a separate network hosting service instances for each customer, and then peer that network with the corresponding consumer network. At this point, each customer can access the service Google provided for them across a peered link. Peering works for networks within same organization as well as across organization. Only restriction is that subnetwork ranges in peering networks should not overlap. Peering implementation provides isolation with connectivity. We talked about VM controller earlier. There is endpoint manager in VM controller that handles all the updates given to it by Fabric Manager. It gives endpoints for each network to a per network flow handler that creates all the flows for that network. Now for peering, we made endpoint managers smarter to understand peering configuration, which make network handlers aware of endpoints in peered networks also. These network handlers then also create flows for sending traffic to endpoints in peered network. But each network can still control what kind of traffic they can receive from peered network through ingress firewall rules. So this is how we provide isolation with connectivity. Peering was implemented as network function with quick feature turnaround by modifications in only the centralized control plane in a true SDN way. There are many more networking features in GCP like multi-NIC, IP aliasing, firewalls that we could not cover here due to time. But before closing, I want to introduce Google Virtual Private Cloud, VPC. Google provides unique VPC characteristics. It provides global connectivity for VMs in multiple regions. so that they can talk to each other over private IPs. It is shareable across multiple projects, and subnetwork ranges can be extended with demand. It also provides access to Google services without traversing public network. There is also full talk later in the evening on this topic. To summarize, here are the benefits of Google Cloud Platform. It provides on-demand access to compute, storage, and networking, high availability and uptimes, high throughput, low latency, network functions as a service. It is built using same infrastructure and innovations that power Google services, and we deliver products at the speed of software. To learn more, these are some of the other talks which will be happening today evening or tomorrow.